the way, analyzing log functions. Here's our next function. We're going to talk about the inverse. I talked about this a bit. Rachel, in the old curriculum, we really did a big song and dance about inverse. And I think if I was next year, I'm going to probably put together a separate mini lesson on how useful the concept of an inverse is. Quick rehash. What's the inverse of plussing 3? Minusing 3. What's the inverse of square rooting? Squaring. Those are operational inverses, but then, Grayson, we talked about the inverse of an equation. We said to find the inverse, if I give it to you as points, you interchange the x-coordinate and the y-coordinate. If I give it to you as an equation, you interchange the x-coordinate, the x variable, and the y variable. Oh, and then you get the y by itself. Oh, and if I give it to you as a graph, it's a reflection about this line. I'm not going to do a big song and dance about that. What we noticed was if I gave you one graph here, the inverse ended up being a reflection about this line here. And if you didn't remember that, don't freak out. What I really want to talk about are these two. How do I find an inverse? I switch the x and y around. And then if it's an equation, I get the y by itself. Now, because of that, switching the x and y around, that meant, Chelsea, that the domain of the inverse was the range of the original, because if you switch your x's and y's around, your y's, which is your range on the original, it will become your x's, the domain on the new one. And the range of the inverse is the domain of the, those actually switch around too. Remember when I looked at the exponential graph, we actually predicted what the inverse would have as its domain and range, and stuff like that. You're probably going to need your graphing calculators out. If you don't have a graphing calculator here, now's the time to sheepishly fess up and swap me for one. Sterling, what type of inversey questions might I ask you? Well, something like number 1 on your test. Number 1A says, draw the graph of the inverse. So underline the word inverse. How do I find an inverse? Switch the x and y around. And it really is that simple if you have a graph. Let me give you an example. I'm going to start with this point because it's on the x-axis. This point is what, comma, what?
3, 0.
What, comma, what? What? Okay, we're going to try that again. Help me out, Dom. This point obviously is what, comma, what?
2, 0.
You know what the inverse will be? 0, comma, 2. I'm going to put a dot there. I'm going to find another point. Rachel, I'm going to move down. This one here looks like a nice one. That point there is what, comma, what? I'll give you a hint, Dom. 3, comma. The inverse is negative 2, comma 3. Negative 2, 3. How about this point here? Oh, are the original 2 points connected? Well, then let's connect them on my inverse. Dunk. This point here, what, comma, what? 4, comma, negative 5. So negative 5, yump, comma 4. Did I graph a point wrong? No, 3, comma. 4, comma, negative 4, negative 4, comma 4. That looks better. Because I was going, wait a minute, it should kind of follow a pattern. I've gone all the way down this way. You know, here's a nice point. 1 over 2 up. 1, comma 2 is going to become 2, comma 1. Have you spotted the pattern? It looks like I can kind of go down 1 over 2, down 1 over 2, down. I've kind of spotted the trend. This in red is the inverse of the black graph that they gave me. If it was a ruler, it'd be neater. I free-handed it, but you okay with that, Zach? Now, here's what I said. For the inverse, what I really want you to remember, Jake, is you switch the x and y around, you switch the x and y around. But Jake, can you read me this third bullet here? It says the inverse can be determined by, read me the second line. Here's the line y equals x. The line y equals x goes through 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Can you see that if you crimped the paper right along that line, they would end up folding on top of each other. They are reflections of each other. That's kind of cool, Oscar, but honestly, I only use that to check that I've done it right. After I've graphed the inverse, I go and I look and I say, hey, that is kind of a little, we need a little reflection, and you think, cool. But I don't use that to graph. How do I graph an inverse? I switch the x and y around. So B asks us to make some conclusions. If the original function goes through 10, negative 16 and negative 10, 24, can you give me two other points on the inverse? You know what? I've been doing the inverse in red. Why don't I keep going in red? What's a point on the inverse? I'll give you a hint.
Negative 16, 10.
Yep. I don't need to graph it to know it. I know it does. Oh, and you know another point on the inverse?
24, negative 10.
Switch the x and y around. Now, I like part C, I like part C, I like part C.
Is part C going to be on the test?
Sort of, and you're going to see why in a second. I do like part C, but we're going to run into something where it no longer works, and that's when we're going to have to invent an entirely brand new function. Part C says, find the equation of the inverse. How did I say to find the equation of the inverse? We still switch the x and y around, but then what? My physics kids will be used to getting stuff by itself pretty easily. Those that aren't in physics, it's equation solving on steroids. So to find the inverse, literally, instead of saying y equals 4 minus 2x, here's the inverse. Wherever there was a y, I wrote an x. Wherever there was an x, I wrote a y. Oh, but then I'm going to get the y by itself. How would I get the y by itself?
Add over the 2.
I think you may have thought it right and said it wrong. Okay, subtract the 4. Sure. X take away 4 equals negative 2y. Kyle? I think you're right, Kyle. Nice and loud. X minus 4 over negative 2. There's the inverse. Or you may have seen someone do this. Because, and those of you that had me for physics, I probably would have done this. I hate having a negative, so I probably would have gone and plus the 2y over first, just to get rid of that stupid negative. Then I would have minus the x over, and then divide by 2. Those are the same equation, because if you actually divide that negative into the top and into the top, the x will be negative, the negative 4 will be positive. It's the same equation as this. I think the right-hand one looks cleaner, but whatever. I'd give you full marks either way. How do I find an inverse? On the graph, switch the x and y around. On the equation, well, switch the x and y around, but they get the y by itself. So far, so good? We just finished looking at exponential equations. Matt, back with me. Matt, what does every single exponential equation look like as a graph? What does every single exponential equation look like as an equation? The x is an exponent. The x is an exponent. So here is our lovely exponential equation. Let's find the inverse. How do I find the inverse? Well, first thing I would do is I would switch the x and the y around. Right, Chels? But then I said, don't stop there. What are you supposed to get by itself?
The y.
The y. What's the problem with getting the y by itself here? Where is the y sitting as an exponent? We have never given you an equation where you needed to get an exponent by itself. In fact, you guys can't do it. In fact, it couldn't be done until we defined an entirely brand new mathematical function. That's today's lesson. It's to deal with this issue. How the heck can I solve for something that's sitting as an exponent? Now, if it's a number, Rachel, that's not a problem. If it's this, hey, how'd I get rid of a squared? Square root. How'd I get rid of a cubed? Cube root. If it's a number, no problem. But if there's a variable up there and the number is in the base, problem. And so we wrote, at this stage, we can't write the inverse. But there was another way to find the inverse, Rachel, and that was to do it graphically. If the graph went through 5, 6, the inverse would go through 6, 5. Maybe I can do as a picture. So, the graph of 2 to the x power, I'm going to do the positive numbers first. So if I put a 0 right there, what's 2 to the 0 power?
1.
So it's going to go through 0, comma, I'll do it in blue, 1. What if I put a 1 right there? What's 2 to the 1? What if I put a 2 right there? What's 2 to the 2? What about 2 cubed?
8.
16. What about 2 to the negative 1? Well, a negative exponent acts like an elevator. 2 to the negative 1 is really the same as a half. And 2 to the negative 2 is a quarter. Remember, we actually did this before spring break. This graph, Carson, would look as follows. It would definitely go through 0, comma, I got to see, how is this going up by 2s? Yeah, it is. So there's 0, comma 1 right there. The numbers don't quite line up, which is kind of yucky. 1, comma 2. 2, comma 2, 4, 3, 4. And 3, comma 1, 2, 3, 4, 5, 6, 7, 8. And negative 1, they gave me a half high. I can certainly graph that one. Is that okay, Amrit? If I connect the dots, we get Matt's graph. Every single exponential graph looks like that. Now, the fact that I have points, Logan, I can graph the inverse. How do I graph the inverse? Switch the x and the y around. So ready, Logan? You're going to graph the inverse for me. Are you ready? Are you ready? Are you ready? Here we go. I notice my graph goes through negative 1, comma a half. What's the inverse going to go through? 1/2, comma, negative 1. 1/2 over, negative 1 down, right there. See if I can make this a bit bigger for you guys. That'll fit. Logan, this point right here is 0, comma 1. What will my inverse go through? You the man. Oh, and my blue graph goes through 1, comma 2. What will my inverse go through? It's almost connecting the dots. It's trickier than that, but yeah. And then 2, comma 4 is going to become, yep. In fact, you know what? I'm starting to see the shape. Are you guys as well? Because 3, comma 8 is going to be 8, comma 1, 2. 3. That red graph is the inverse of the blue graph. It's the graph of the mystery function that I wish existed. And this is weird because I don't even know what the equation is, but I can tell you what its curve has to look like. Has to, Rachel, look like that. Otherwise, we're sunk. Oh, by the way, remember Jake told us that the inverse function is a reflection about the line y equals x? Just to show you that that trick does work. Here's the line y equals x. It goes through a 45-degree angle. 1, 1, 2, 2, 3, 3, 4, 4. If you folded the paper right along that, yeah, they do overlap. So, yeah, I did it right. Okay? But, oh, and by the way, you'll notice I didn't even bother filling in the points. I actually got it right from the graph, which is kind of cool. But that is the graph of x equals 2 to the y. What's the problem with x equals 2 to the y? Can we even graph that on our graphing calculators? No, because our graphing calculators automatically start up by saying y equals, not x equals. So we really hit a wall here. Or have we? B says, state the equation of the line of symmetry. That's the fancy way of saying what's it reflecting about. It's still reflecting about the line y equals x. You know what, Mr. Dueck, since you drew it in black, why not write it in black? Turn the page or next page over. Grayson, I hope I've convinced you that, first of all, there is an inverse for the exponential because we just graphed it, and that it would be useful because it would give me a way to find or solve for something that's sitting up there as an exponent. We're going to give this mystery function a name. We're going to call it the logarithm, or the log for short. And it's defined as the inverse of a function, of an exponential function. And the notation is going to look a little weird at first. Don't freak out. This is one of the few times I'm going to say, memorize what the numbers mean. Are you pressing your log button, or are you trying to graph something? Yeah? Okay. So your graphing calculator does have a log button. Okay. Get it out. What's the log of 0? Oh. Hey, wait a minute. Look up, look up, look up, look up, look up. Look at this red graph. Does it actually ever touch 0? That shouldn't have surprised us. What's the log of 1? I'll bet you it's 0. Because that's my x-intercept on, is it? Okay. What's the log of 10? What's the log of 100? Not 10. Yeah, it's an exponent, because there is an exponent associated with 100, isn't there? What's the log of 1,000? What was the log of 100? Log of 100 was 2. What's the log of 98? Hopefully really close to 2, but a yucky decimal. So here's what you're saying. If you go log of 98, what you're also saying is this: 10 to the power of 1.991226076 is 98, or really close because I had to round up. By the way, much like most square roots that went on forever, most logs go on forever without repeating. They're irrational. Except it's more profound than that. Your calculator only has log base 10. I'm going to teach you how to do log any base. So back to here, put your calculators down. The inverse of the exponential function with base 2, the inverse of y equals 2 to the x, is y equals log base 2 of x, which is also what we wrote here, but I hand wrote it just to show you how you handwrite it. Here's what this means. As soon as you know this, you also know that y equals 2 to the x. One implies the other. Okay? As soon as you know this, you also know that. They mean the same thing. This is the inverse that we wanted, but Sterling, this is how we write it. In general, we write things in logarithmic form rather than having the x by itself, because the logarithmic form allows us, Rachel, to get the y by itself. So if I want to show the inverse of y equals b to the x, it's going to be log base b of x. Here's the equation. Here's the domain. All x is greater than 0. Stay on this page. Remember, the exponential had all y's greater than 0? And we said for the inverse, the domain and range will switch. So that shouldn't surprise you that the domain is all x is greater than 0. Oh, also it says the domain, sorry, you guys can ignore that. That sounds like it's saying x is all reals. It's not. It's using set notation. Don't freak out. The base has to be positive and can't be 1. And the reason we've said that is, what's 1 to the 3rd? What's 1 to the 4th? What's 1 to the 9th? What's 1 to the millionth? 1 doesn't behave like any of the other exponents. It doesn't work. So we say, by the way, log base 1 is not going to get you anywhere because it doesn't follow the normal exponent rules. The inside of the logarithm, x, called the argument, and the argument can never be negative. Look up, look up, look up. X can never be negative. Look at the red graph. It's always positive. You can't plug in, if you try it, the log of -3, you get an error. If you try the log of 0, you get an error. So here's the two graphs that we just did on the previous page, but this was done with a computer. This graph here is actually y equals the log base 2 of x. You can label that. And now we're going to complete the table. Now I'm going to, Carson, do something a little weird. Giancarlo, you going to make it? You woke up in a hurry there. Ty is long gone. You might want to give an elbow. Oh, no, he is alive. Okay. You guys have the graph in front of you. I've told you that if you know the original, you automatically know its inverse. I'm going to scroll up so that I can't see the graph, but I'm going to fill everything in, not by using the graph, but, Darian, by using what I understand of how inverses work. They switch the x and the y. So first of all, Matt, what does every exponential graph look like? Matt, what does every exponential graph look like? Or? Okay, so we said this. For every exponential, right? Here's what that means right away. Since the log is defined as the inverse, Grayson, I know the range is all reals. Check the graph. Is that right? Does the log graph go all the way down and then keep going up? And you'll notice I didn't need to look to confirm that. I know that. I remember that the range of the exponential was everything above 0. Here's what that means, Laura. I automatically know the domain is everything to the right of 0. I'm literally switching the x and the y around because that's how you find an inverse. What I'm really saying is if you really understand inverses, you can cut your memorization in half. I've memorized this one really, really well, and I can derive this one in 1 second of thinking every time. What was the x-intercept of the exponential graph? It's a trick question. What was the x-intercept of the exponential graph? It's a trick question. You know what that means, Julia? There's no y-intercept of the log graph. Go look at that log graph. Does it ever cross the y-axis, or does it ever touch the y-axis? Nope. But I don't need the graph. I'm just using my knowledge of the inverse, Darian. The graph is kind of like a handy crutch backup, but I can do it by being medium clever. What was the y-intercept? The y-intercept was 0, a, in this case 0, 1. You know what? This is going to have an x-intercept of 1, 0, and I switch the x and y around there too. Am I right with all this that matches the graph? And the exponential had a horizontal asymptote. I bet you the log graph is going to have a vertical asymptote of x equals 0. The y-axis, I'll bet you, is a... Yes? See, so, Ashley, you can memorize both of those. Have I tried to give you a fairly easy way that if you just understand the first line, and I've had Matt doing the stupid song and dance for that reason, you can derive the rest? Okay. Notice the following. Notice the following. If your exponential went through 3, 8, that point becomes 8, 3 on the log graph. Here's what that means. Apparently, the log base 2 of 8 is 3. That's the only way that I can fit 8, 3 into that equation. That's the same as saying, and once you write that down, I'd like you to look up so you can see how these numbers move around. That's the same as saying because that is true. 2 to the third is 8. Jake, when I see this, in my mind, I imagine this to that exponent equaling, I kind of see these both at the same time. You show me one, the other just pops into my brain. They're that related. So the point 3, 8 indicates that 8 equals 2 to the third, or I usually write 2 to the third equals 8. How do we graph that? Now we got a problem. What's the base of this logarithm right here? Your graphing calculator only has one base 10. And the reason is, turns out there's something called the base change law. You can change any base into any other base. How? Get your graphing calculators out. If I want to graph log base 2, go to your graph menu. Delete any graphs that you have there. And then once you got everything cleared and ready to go, kind of look up and make eye contact so I know you're good to go. We're all good. My calculator only needs base 10 because the way to convert base 10 of a log to any other base is you go like this. Log x, that's base 10. But if I go divided by log 2, that will convert that to base 2, turns out. Double check your view window, go Shift F3 and go View Standard. And if you hit Graph, there's our log graph. If you didn't get that, kind of give me a wave and I'll come and see what the typo was. Okay. Okay. Look up, if you want to get the same graph as we had on the previous page, if you go back to the graph menu, F6, Y2, you can graph 2 to the power of x, and that will give you the exponential curve and the inverse. The only problem is going to be it's not quite going to look like the way it looked on the previous page. It's not quite as symmetrical, and this is something I need to point out to you. The reason is, what shape are your graphing calculator screens? Are they square? Because they're rectangular, they actually distort every graph. They don't actually graph on a square grid, they graph on a rectangular grid. So, if you want it to be a square grid, they have programmed that in too. If you want this to look all pretty and symmetrical, if you go to your view window, Shift F3, okay, the initial one, this is the one that they've pre-programmed, which actually makes this a square grid. If you hit F1, it should change it to negative 6.3, to that. And if you store that and now hit draw, it's now symmetrical about the line y equals x, but it had to chop off part of the graph to do it. Which one's right? Well, they both are. The message I'm having for you, Oscar, is with the technology that we have, we're limited. Okay? Says, exploring the value of b. Okay. Says, in each of the following, sketch the graph on a graphing, blah, 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 blah. Use the graphing calculator with this window. Okay, you ready? Let's use the technology. Get out your graphing calculator. Again, clear any graphs you have here. Oh, I don't want that. Delete. Yes. Delete. Yes. We're all there. And before we do anything, now they've given us a view window. So go Shift F3, but we're going to type what they want us to. And the way they know that almost every graphing calculator has X min, X max scale, Y min, Y max scale. So this first number is the X minimum, type -1. What do they want the maximum X to be? 11. What do they want the scale to be? 1. Ignore the dot thing. That is a resolution. Whatever it says is good. Go down 1. I'm covering mine. What do they want the Y min to be? It's in front of you on your calculator. What is it on your textbook? -4.
Then +4.
+4.
And then 1.
Okay. So Grayson, that is how they can tell you what view window to use so that your graph looks like their graph. Because again, these are little rectangular screens. You can zoom in all over the place, and sometimes you'll be saying, am I right? Mine looks different. Maybe it's because you've distorted it. Okay? So you all got that? Let's go back to the graph menu, F6. Or execute, sorry. Enter to store. All right. I'm going to move this guy back over to here now. Yoink. The first one they want me to graph is y equals log base 5 of x. How am I going to type that? Log x divided by log 5. Then hit draw. What I now want to do is find some specific points. To do that, we're going to hit gsolve, F5, arrow sideways, F6, and then we want a y calculation. We want to give it an x value and have it tell me a y value, which is F1. And hopefully that comes up. I hope. Yeah? If that doesn't, now's the time to call me. The first thing we want to find is when x equals 1. So can you type 1? This graph goes through 1 comma what? Sorry? Oh, okay. So one of the points on here is 1 comma 0. And the other one it wants us to check out, okay, here we go. G-solve, arrow sideways, Y-calc. It wants us to see what you get for an x value of what? 5. What do you get? So log base 5 of x goes through 0, 1. Sorry, it goes through 1, 0 and 5, 1. Goes like this. I'm going to change colors. I'm going to do 1/3, the next one in red. So now it wants me to graph y equals the log base 1/3 of x. Okay, go back, hit F6 to get back to y equals. How do I do the log base 1/3 of x? It's going to be, if I go up arrow and I'm just going to edit, it's going to be the log of x divided by the log of, I'm going to delete the 5, I'm going to go 1 fraction button 3. Remember we learned how to type fractions in the probability unit, right? And I hit graph. Oh. Oh. Okay. G-solve. Arrow sideways. Y calculate. Again, I'd like to find out when x equals... Hang on, let's pause. No, not 1 divided by 3. Use the 1/3, use the fraction button. Or if you're going to go 1 divided by 3, Darian, you have to put the 1 divided by 3 in brackets. That'll also work. Sorry, what? Okay, hang on, let me back out of here. On this screen, log x divided by log 1/3. By the way, if I wanted to graph log base 7, it would be log x divided by log 7. If I wanted to graph log base pi, it would be log x divided by log pi. That's why your calculator only needs the 1 log button. They didn't have to put every single base. The one that your calculator has by default is base 10, because we have 10 fingers. Is we okay? Yeah. Okay. So draw, if you haven't already. G-solve, arrow sideways, get to this screen. I think it still goes through 1 comma 0, does it not? So it still goes through right here. Ah, but what about when you put a 1/3 in? What? Let's see. G-solve, 1 fraction button 3. When we're 1/3 high, when we're 1/3 over, we're 1 high. You know what? Kind of right about there. Kind of sort of does that. Okay. I'm not going to do the third one. Here's what I want you to realize. Matt, what does every exponential graph look like? Or, okay, hold that one. If your original exponential graph, you can go back down if you want, sorry, is a growth graph, look up, look up, look up, look up, look up. No, look up really means look up. If your original graph is a growth graph because the base is bigger than 1, your log graph will look like that. If on the, and we're going to write this down formally, if on the, same colors, Mr. Dueck, if on the other hand, your original graph, your original log graph was a decay graph, then your log graph is going to look like, oh, that's terrible, like that. That's the two different types of graphs I can get. I can get one coming up here and going like this, or I can get one starting down here and going up. This is the sort of equivalent of the negative that flipped the graph, kind of like that, but not quite. So, complete the table, it says. You'll notice right here is where things change. We have bases bigger than 1 or fractional bases. Everything has a domain it's always to the right of the y-axis. Because these are log graphs, every log graph has a range, all reals, all reals, all reals, all reals, all reals. Every one of these, I'm going to skip a column, every one of these has no y-intercept. What was the x-intercept that we kept running into here? 1 comma? Yeah. Every one of these is going to have an x-intercept of 1 comma 0, 1. That's because every exponential had a y-intercept of 0 comma 1. Every one of these has a vertical asymptote. Every one of these gets closer and closer and closer to the y-axis. The y-axis as an equation is x equals 0, x equals 0, x equals 0, x equals 0. And what's the x value when y is 1? So what's the x value? What's the x value? What's the x value when y is 1? Well, for base 5, it was 5 comma 1. For base 3, which is this graph here, it's 3 comma 1. Oh. So, for base 3, it's 3 comma 1. For base 5, it's 5 comma 1. What do you think for base 1/3? 1/3 comma 1? 1/5 comma 1. Generalize it. For base B, it's going to be, there's your, I can't call that an intercept, but that's a point. Okay? Then, if you draw two little fake graphs here, when the bases are bigger than 1, you're doing that. When the bases are fractions, you're doing that. This one, Matt, is tough for me to have somebody act out. I can't say all log graphs look like, whoa, or whatever, but it's this, along the same lines. Yep. Quick like a bunny. How much further are we going here? It is a huge one, so I think I'm going to pause temporarily and I'm going to give you a start. I think for now, number 1, number 2, number 3, number 4, 5 is good. And then I think it's going to be I think 5 is good. Let me double check. Sorry, I got to take away. 4 is going to be next class. I'm going to just erase it. Right now it's 1, 2, and 3 because I haven't yet talked about what happens when you put a number in front of the log. Although you can play with the graphing calculator and figure it out yourself. But, well, you know what? 4a, you can do that one. No, 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 no. I think you can do number 8. We'll kind of pause there.